Hi, everyone. Thank you for attending this session. Here's my topic talk. A lot of contributors. So surface acoustic waves are used in many different applications across various devices, most notably the touchscreen. But they are well understood and they excite with great efficiency using interdigital transducers, which is the bottom right picture. So spin waves, just the basic setup. Uh, all the atomic magnetic moments are aligned in a film, and these moments create a net magnetic field. The precession of these magnetic moments can create a spin wave-like pattern, and there are three different cases. The spin wave will propagate to the right, K value, but the magnetic moments can be aligned in at least three different cases, and of course they can be oriented whichever way you like. So at least for these three basic setups, you'll have three different spin wave dispersions. For the backward volume spin wave, notice that as the wave vector k increases, frequency actually goes down. It's very unique. So in the homogeneous case, where the magnetic field is kept constant throughout the whole film, we do like theoretical case study with YIG and GGG. So you can excite surface acoustic wave with the IDT or with the backward volume spin wave with an antenna. And you'll see that when they do couple, they'll propagate in opposite directions. YIG is great for its low magnetic damping, and it still has very good acoustic properties. So here's the spin wave dispersions again. Surface acoustic wave, linear, backward volume spin wave comes down. And right here where they cross, they will couple. Magnetoelastic interaction. I'll note the coupling rate is GME, and this frequency gap is 2 times the coupling rate. I highlight this frequency gap because it's very unique where they cross. It actually opens up a forbidden band gap frequency where if you were to excite a wave of this frequency, it would be like immediately converted into the other wave. Again, this situation is very unique for the backward volume spin wave, as it was not happen in either of the other cases. So how I calculate the coupling rate, magnetoelastic energy density, plug in wave profiles for the acoustic wave and for the magnetic spin wave. I know I'm throwing a lot at you there. Here we have this long expression for energy and this integral, more or less constant, is the coupling rate. We have a magnetostriction tensor, magnetic moment, profile of the acoustic wave and profile of the spin wave, which is what the integral is dependent on. So it's the overlap of these profiles that give us our coupling rate. So you can, so just to complete it, we have the energy and the wave equations of motions in the first derivative. I use this to calculate the spectrum, which you'll see here. So, yep, we have our band gap opened up here. I'll expand that. In this case, for the parameters I've chosen, we have a band forbidden frequency band gap of 34 megahertz. Again, you can do many interesting things with this band gap, as I'll show one example later on at the end. So here are the coupling results. I show how coupling changes with an increase in the magnetic field for various thicknesses. Again, it comes back to the overlapping wave profiles. As we increase the magnetic field, notice what happens to the surface acoustic wave profile. It will shrink as the wave vector increases with the magnetic field. And this wave vector, as it increases, it becomes shorter and shorter in wavelength, and the surface acoustic wave becomes more localized. That's why when we look at the YIG thickness, this is really thick, this is really thin. As we go to thinner films, The spin wave profile changes as well, but we'll have more localized shared energy coupled between them. So for the inhomogeneous case, where the magnetic film is not constant in magnetic field strength. So the YIG film will be kept at a bias field of H, and then I'll place a wire on top of the YIG film, or like hovering above, and that'll give us a change in the magnetic field right above where the wire is in the YIG film. So this is what it'll look like. In the YIG film, it'll be kept at this constant magnetic field. We'll have our wave dispersions, the surface acoustic wave and backward volume spin wave. Note, I am exciting a surface acoustic wave at a frequency F naught. The backward volume spin wave dispersion does not interact with that frequency just yet. As the surface acoustic wave propagates through the YIG film, it'll reach this point where the magnetic field is raised because of the wire. When we're right under the wire, then the excited saw frequency will interact with the backward volume spin wave, and we have that forbidden band gap frequency where the two waves interact. And then this is, you can say, the coupling region, the band gap. You can think of it, just for simplicity, as the diameter of the wire. So how large the wire is does affect how well it couples. So here, just to show our conversions, this is in K space, and we have to convert that to real space now. There's more math. After a proper Fourier transform and Taylor expansion, we get our terms for the wave equations, and then you can see that we have our change in magnetic field. Only when this change in H is 0 do the waves actually couple. So here, okay, cool. So I have a set of parameters here. Surface acoustic wave excited at 567 megahertz. We have a wave vector. And then, so this is for a very small wire. Oh, okay. So the surface acoustic wave comes in from the left and is converted to a backward volume spin wave. For the very thin wire, the coupling rate actually doesn't have enough time to completely change the surface acoustic wave to a backward volume spin wave. And then if okay, movie 2. So I've widened the region of the wire diameter, and the surface acoustic wave converts into a very tall spike of the backward volume spin wave. It becomes taller because of the change in their speeds. The backward volume spin wave is slower than the surface acoustic wave, but you can see that the power is much more amplified. And then just for movie 3, where we have a very wide wire diameter, the surface acoustic wave comes in, and the backward volume spin wave, the packet actually stretches out a little bit asymmetric within the tail. So there does become a point where it just becomes wider instead of more of a concentrated peak of power. Movie. Okay, there we go. And just in conclusion, you can see we have shown efficient coupling between the surface acoustic wave and backward volume spin wave. The magnetoelastic interaction between these waves opens up prohibited band gap, which is very nice in a lot of our devices that we like to work with. And we have a scenario of exciting a surface acoustic wave into a backward volume spin wave. And of course, this can be done vice versa. If you have an antenna, you excite backward volume spin wave, which can be converted into a surface acoustic wave as well. And that would be it. Thank you for your attention.
Thank you very much for your nice talk, Nicholas. So yeah, we have some time for questions. The floor is open. if you want to type it in the chat, or if you'd like to raise your hand and we're calling you to unmute. So first question in the chat from John is, pure exciting surface acoustic waves consistently, could they interact with backward scattering spin waves coming from your wire excitations? So looking at slide 40, I think.
Slide 4. Let's see. I haven't, will they scatter? I would say maybe not, because the backward volume spin wave is excited within the magnetic film of the YIG, but the YIG is at a different magnetic field where the surface acoustic wave would probably not feel it. I would say no.
So if you have any follow-ups, feel free to ask John. I have one quick question. Looking at the systems you described, I mean, it seems like something that could very much easily, well, maybe I don't want to say easily, but could be experimentally realized. Have you guys done any experimental work or collaborated with experimental groups to test these simulations?
We've been in contact with a few people. No one's gotten around to it, but again, if anyone does want to try some tests, we ran just a couple numbers, radius of the wire, and you can see how much it'll shift the magnetic field and the current you need, if anyone does want to try it. I think you would obtain some interesting results varying the surface acoustic wave frequency, but that, of course, that's a different thing. Well, you can vary the antenna.
Yeah, there were some really interesting experimental work on similar systems in the earlier sessions quite a few hours ago. So I was just curious. This work, I mean, it seems like your theory is like quite a bit unique. So compared to what they were looking at.
Yeah.
If we have any other questions, we have time for maybe one quick one. Don't see any hands up or in the chat. Maybe I can ask one more quick one. So can you talk just quickly a little bit more about this prohibited band gap and sort of what sort of advantages it might lead to for applications and devices?
Sure. Like on this slide at least, obviously it could act as a filter or signal conversion. Obviously, if the wire is off, the waves will not convert or interact. So some signals could pass through, or if you turn the wire on just for like a quick or microsecond, then the waves would interact. And then you could have a conversion of, I think there are some like phase changes too when they convert. I haven't looked too much into details there. But that's because of the change in velocity between the two waves. One is faster than the other.
Okay, thank you very much, Nicholas. I think